die. Then the postdoc at Caltech and people moving to McGill this year. Done work in a variety of domains, from accretionist to tides to neutron stars, and today he's going to tell us about resonant shattering of neutron star crusts.
Thanks, Francois. So I'm going to talk to you guys about this stuff today. This is a paper I did last year. I've got some more recent stuff, but it's not quite polished enough for a talk yet, so we'll go with this. This was actually a really fun project to work on because it's basically just a bunch of my friends and friends of several of the people in this room. Jocelyn Reed is a professor at Cal State Fullerton now. She and I went to undergrad together. Tanya and Rosandra, we went to grad school with me and several people in this room. And Tony was a all at Caltech. So we all got together and we decided we wanted to write a paper together, and surprisingly we found something good to write about, which usually doesn't happen. But it was right. So I'll talk about resonant shattering of neutron star crusts. Okay, so first, a couple of background information. Okay, so we know neutron stars come from relatively massive stars, the end product of stellar evolution for relatively massive stars, somewhere between 8 and 20 solar masses, depending on metallicity, or so or told me at one point. And more massive stars become black holes, and less massive stars become white dwarfs. You guys all know this? Okay, so the structure of a neutron star has a very small atmosphere, followed by a relatively small crust, maybe a kilometer or so thick. Then outer core and then inner core. The outer core is superfluid, superconducting superfluid. The inner core is probably going to be superfluid, but you don't really know. There are some quark and strange star core theories. What I'm going to be focusing on is the crust core interface, about right there, and that's at about 10 to the 14 or so grams per cc. Okay, so I'm going to be. So we know about. We know of a few neutron star binaries that have been observed in the galaxy. The most famous is the Pulse-Taylor pulsar. Close second is the binary pulsar, which is no longer a binary pulsar now, given that that's processed. One of them is processed out. But and the Pulse-Taylor pulsar, we know, decays due to gravitational waves. So we know that, and this is actually probably the best indication of gravitational wave emission that we have so far. Problems, soon to be not, hopefully in a few years. But so we know that the orbits of binary neutron stars go around and decay due to the emission of gravitational waves. Here, my neutron stars are blue and my gravitational waves are red. Okay, so I probably don't need to go through this for here what gravitational waves are. So we'll skip that. Okay, so, and we can probably skip this stuff. These are different ways of detecting gravitational waves. We have LIGO / advanced LIGO / Virgo. We have pulsar timing arrays, which look like bow-fighting octopus. And we have LISA, which we don't really have. But maybe eventually we'll have some star LISA, where star is some letter. Okay, so what's of interest here is advanced LIGO / Virgo, and the number of neutron star, or neutron star black hole binaries that you can expect. Now, this table is sort of the rates that you might expect for the number that we would see in the initial LIGO per year. So you can see that basically, while there was a possibility that we could have seen a neutron star, black hole binary merger, it wasn't that likely in the reasonable cases, while initial LIGO was turned on. Advanced LIGO should have a better chance of seeing these, given that the so-called realistic rates are about 40 a year detected neutron star mergers. Take this all with a grain of salt. The way I like to put it is that these rates are a lot like sausage casing. I don't know what goes into them now, but they used to be full of crap. So that's the best we can get, but it's not that great. Okay, so we are looking in the frequency range for initial LIGO of somewhere like to tens to hundreds of hertz, okay, up to almost kilohertz. Okay, so in this case we have a binary. Sorry, moving this way. Binary neutron star, and it's spiraling in, and it emits a gravitational waveform. And here is basically the PN part of the in-spiral cloud. And so we can zoom in a little bit. At about a few seconds beforehand, it's at tens of hertz. And right before the merger, it zips up in a sharp to several kilohertz. Okay, before merger. What else happens after a merger? Well, presumably, this is the leading model. Merging neutron stars are the leading model for what are called short gamma ray bursts. Now, that wasn't a short gamma ray burst because it wasn't pointed at us. Right? We wouldn't have seen that as a short gamma ray burst. But if you're sitting on a jet, you would have seen this big burst in the gamma rays, and that's thought to be, these merging neutron stars are thought to be the source of this. Okay. So short gamma ray bursts have energetics of 10 to 50, 10 to 51 in total, and they occur, they're called short because generally they happen in a few seconds. Okay. Now there's some evidence that long gamma ray bursts can also be that long gamma ray bursts have a population that's also that short, but we'll not go into the details there. But basically, there's a population of gamma ray bursts which are short, which presumably come from nearby galaxies or this galaxy. The leading progenitor for these is neutron star or neutron star binaries or neutron star black hole merger. What happens is they emit gravitational waves until they collide. Black hole with an accretion disk forms. The rapid accretion sends a jet out along the axis, and if we move down here, where you can look down the barrel, that would look like a short gamma ray burst. Okay. We detect short gamma ray bursts with Swift map, Fermi GBM, or Suzaki WAM. Okay. Now, a couple of years ago, there was a paper by Troja et al., which looked for precursors to short gamma ray bursts. And they found some candidates, these little blips, basically, that are outlined in blue. Now, these two, I think, the top and the bottom one, are supposedly 5 sigma. So I have a hard time convincing myself that's actually 5 sigma. And this one is like 3 sigma. However, that's what Neil Garrell says. And he knows a lot more about diffraction than I do, so I'll believe him. And these guys basically are little blips in the gamma rays a few seconds beforehand. So here they're 2 seconds roughly, and 10 seconds, and this one is 25 seconds before the main burst, which triggers the monitor. So what happens is Swift or other burst monitors sit around waiting until their threshold is passed, and then they sort of keep about 100 seconds on the other side. And so that they just these guys sifted through that data looking for a precursor. So you wouldn't have seen anything several hundred seconds before, just that the data is not stored. Okay. So the question becomes, the question that we wanted to answer was, what happens a few seconds before a short gamma ray burst that could give you a precursor? Okay. What happens there? 1 to 10 seconds before. Well, there's a bunch of different things. I'm sure Maxim could tell us a lot more about this. But you could have a magnetic field interaction, basically a unipolar inductor, where you are moving one neutron star through the magnetic field of another neutron star. And that can drive X-ray and radio emissions. But in order for the luminosities to be comparable, so here you have luminosities that are about a tenth to 100th of the main burst. In order for these luminosities to be comparable to the main burst, you need a V field greater than magnetron strength. So it's unlikely, though this should certainly happen, it's unlikely that this is the source of the precursors. Okay? This would also look like basically a slow ramp up, not sort of a sharp burst. Perhaps there's early central engine activity, though needing to delay for a few seconds is kind of hard to imagine how that could happen. And in a similar vein, you may be able to have a hypermassive magnetron that sort of gives you an outburst for a few seconds beforehand and then collapses collapses down and forms the main engine. But both, it's very difficult to get 2 to 10 seconds. It's very difficult to hold off for 2 to 10 seconds. So there was another option, crust cracking. So Chris Chanek looked at this in 1992, whether you could get crust cracking on a neutron star. And we'll look into this in a little more detail. In order to fracture the crust, we need to know sort of how the crust will behave as we stress it. And so this is a molecular dynamics simulation from Chuck Horowitz and his student. And basically here, they've taken a volume of material in a Kumon lattice and then sheared it. And found basically with the breaking strain, the strain at which the material fractures is around 0.1-ish for different lattices. And that it fractures when you strain it past this point. Now, you have to take this also with a big grain of salt because, looks like salt. You have to take this with a big grain of salt because in order to resolve this numerically, they have to shear this at a really, really high shear speed. Otherwise, you're not going to, it would take too long to compute. And if basically the shear speeds here are like, essentially shearing at the speed of light. And if you punch anything hard at the speed of light, it's going to shatter on you rather than even if it would normally classically be form. So they claim basically that you get a fracture, but it's not entirely clear that in a normal case you would. So take that with a grain of salt. I'm going to assume it does fracture though, because that's sort of the whole point of my talk. But keep that in mind. I probably shouldn't dissuade you before I make my case, but if we want to be honest, we have to keep that in mind. Okay, so from here we'll assume that for tidal crust cracking we need delta R over R, a breaking strain of about 0.1. Okay, about a tenth. Okay, that's pretty big. Most material is not even close to that. So how much energy can we get out of the crust if we fracture? Okay. Well, we can estimate that. We know the height of the crust is about 1 kilometer, we know the densities, and we know the shear modules. Shear modules is about 10 to the 30 roach per cc. Then we can guesstimate the energy contained in a fracture here, or basically in the crust, I should say, at about 10 to the 48 ergs. And when we get a fracture, it's about the distance, the separation distance between 2 neutron stars to get a fracture from direct tidal forcing is about is only a few times the radius. That's pretty close. Okay. Question is, when does that happen? Does this happen in 2 to 10 seconds before merger? I mean, given that it's that close, you probably already know that it's not going to be the case. So you can estimate this. So here is delta R over R as a function of frequency, and you can see in order to get to 0.1, you need to be pretty high frequency, kilohertz, several kilohertz. This is for just different cases. And here you can see, it's actually off the chart, but you're basically at a few milliseconds before the coalescence time. So direct tidal cross cracking either doesn't happen or happens just before the merger. So it can't match up with precursor. Okay. What else can happen? Well, we have basically a tidal force, a periodic tidal force, that's sweeping up through frequency. But we need it to sort of do more than it sort of can directly do by just forcing. Well, how do we, if we have a small periodic force and we want to get a big result, what can we do? We can cause something to shatter, cause something to resonate and then shatter. Okay. So that's what we're going to talk about. So in order to get a tidal resonance, we need a couple of ingredients. Well, first we need a normal mode that we can excite. Of course, neutron stars have normal modes. All stars have normal modes. And neutron stars are no exception. We need a large amount of energy transfer from tidal resonance. And that energy has to be transferred into a mode that strains the crust. It couples to the tidal field strongly, in order to get enough energy, and it hits the resonance well before the merger. So you need a frequency that's below a kilohertz. So to get into detail, we treat these perturbations a la McDermott and Resonant and Wilbright, except we use a TOV background. This is approximation, so you can't quite take our frequencies to heart, but they're close enough for our purposes. Okay, so the first mode that you might expect would work, or that could work, is the G mode, the core G mode of the star. So that couples to the tidal field. It's an LEV2 spheroidal mode. It hits the resonance well before the merger. It's got frequencies in the around tens to hundreds of hertz. But it doesn't strain the crust. It basically drops to zero inside the crust. So we don't get any, there's no chance of that will fracture. Okay. You might expect that maybe the toroidal shear modes in the crust would work, because that strains the crust a lot. Okay? It also has resonant frequencies around 10 to 100 hertz, but it's not a spheroidal mode. It's a toroidal mode, so it doesn't couple to the quadrupolar tidal perturbation. Okay. Well, the thing that couples the most strongly to the tidal perturbation is the F mode, fundamental. Okay. That definitely also strains the crust. It extends into the crust very strongly. Okay. It couples to the tidal field, but its resonance is in the kilohertz. So again, this won't actually do anything until right before merger, or it may not even have a chance to do anything. Okay. So, and this is a leading thought because you can see I made this one myself. But this is the interface mode, the L2 interface mode. Here, basically, what happens is the core of the star is deformed elliptically, sort of just like an F mode, whereas the crust sort of shears out of the way. That's the way to think about it. Okay? So the crust here shears out of the way, while this thing sort of bulges out. Okay? And this only exists, and part of the restoring force here is the shear, the fact that the crust has a shear modulus. That's what makes this work. Okay? And this only exists because there is a transition from fluid to solid in the core. Okay? So this strains the crust, clearly. It couples to the tidal field, because it's an LEV2 mode. And it has resonant frequency in the tens to hundreds of hertz. So this may be the lone mode, okay, if it couples strongly. So the mode frequency should be twice the orbital frequency at which it's resonant. Okay? It should be, which is equal to gravitational wave frequency. We want to transfer a lot of energy into this mode so that we can excite it to a very large amplitude. Note, of course, here that the neutron stars don't get tidally locked. And in one particular example, the Shin-Hansel equation state, the frequency is about 105 hertz. That'll be my canonical example, though we do actually different equations of state later on for different frequencies. Okay. Here, this is the Gaussian perturbation, and U here is the radial displacement, and V is the horizontal displacement. Just so you can idea what it looks like. Here I've basically just plotted out that the strain in the crust, and yellow is large. So basically the strain is maximized. So here the companion would be right there, or over here. So basically at the base of the crust in the plane is where the strain is the largest, and that's where the fracture would occur. Okay, so let's ask, can tidal resonance break the crust? Do we have enough energy in the system in order to fracture the crust? Well, we can estimate this. We can basically look at the eigenfunction, set the strain to be the breaking strain, and look at the amount of energy that's in that mode. And that's about 5 times 10 to the 46 hertz for this Shin-Hansel equation state. Okay, and for a breaking strain of 0.1. How strongly does it couple to the tidal field? We can basically do an overlap integral. We'll go into the details. But when you take this overlap integral and you plug it in here, we get a very large amount of energy transfer. If everything stayed linear and nice, you'd be able to transfer about 10 to the 50 hertz. So way more than enough energy. 4 orders of magnitude more energy than you need to fracture it. Okay, so it looks like we have enough tidal coupling.
As a picture, this is as you're sweeping through, you have enough time
Yes.
to transfer the energy.
Exactly. So I didn't talk about the time of resonance is basically the geometric mean of radiation reaction time of photons. Okay. So what happens next? So you fracture, you cause a fracture in the crust. Okay. So the orbit transfers some energy via resonance into the mode. Okay. The mode hits this breaking energy. That fractures the crust. Okay. That will generate a bunch of seismic waves in the crust, in the solid crust. And that energy sort of rattles around. It can't effectively couple to the magnetic field and get out because it's relatively low frequency. You can estimate the rough frequency of the peak energy of this by looking at the shear speed and the size of the slip plane, right? And that's going to come up to a couple hundred hertz, which is not large enough to couple. These are the impedance matching calculation you do that Peter and Orr did ages ago. That you can show that the energy just can't get out very efficiently. So this energy will just rattle around inside the crust. But these things, this will quickly heal, and you have plenty of time to keep driving this thing in resonance and dumping more and more energy through fractures into the crust. Eventually, the energy contained in the crust, and the seismic energy, will hit the elastic limit, where basically every part of the crust is strained to breaking strain, is the way of estimating that. And that's about should be 10 to the 48. Okay. I screwed up on the number there. Okay. So I think this should be 10 to the 48 ergs. And once that limit is hit, the whole crust shatters. Okay, basically, it can't support its own the oscillations anymore, and the whole thing should sort of break.
What's the dominant linear damping mechanism for this one?
The dominant damping would probably be right at the interface. There's probably a lot of viscosity as you're sliding this stuff back and forth. So, and it's definitely above any sort of fluid.
And then roughly how much time left is there in the spiral? What do you think this is
A few seconds. It's driven so hard that we don't think damping really matters. But you have to be a little bit careful here that the way, what's more dangerous, or what may make it not work is how it sort of responds non-linearly, whether it shifts in frequency, which way it shifts in frequency. If it shifts down, then we're in trouble, then it'll pop out of resonance. If it sort of shifts forward, up in frequency, then we can sort of ride a little bit more and be okay. But that's
along the same line, this is going to be pretty highly nonlinear. Yeah.
Yes.
So there's a couple of other sorts of moments.
Probably.
The drain energy.
Yeah. I mean, what we're counting on here is that the driving is much stronger than the damping. But that is a source for it. So basically, here the seismic energy gets scattered to much higher frequencies once it shatters. Okay? Frequencies along the shear, whatever size scale that you're scattered, that you shatter to, divided by the shear speed divided by the size scale of the shatter. Okay? And that can couple. That's going to be much higher frequency, and that can couple to the magnetic field. The magnetic field gets shaken. In one case, if you have a very strong magnetic field, greater than 10 to the 13 Gauss, then you can carry that emission off without any noise. If it's weaker than 10 to the 13 Gauss, which it probably is, these are old neutron stars that have spiraled together, then we can kind of guess what happens. And part of the reason I wanted to come here was to talk to the experts in the room about this emission mechanism, because this is literally hand waving the magnetic field. Where if you take the magnetic footprint and you shake it back and forth, you're going to generate a lot of transverse electric field. And if you can generate, if that can accelerate particles to above 500 keV, then you can spark a pair of photon particles, and that will just blow out nicely. Unfortunately, we can't really make a prediction about what the spectrum looks like if we don't know what the baryon limit is. If you're popping off photons with 100 keV, you can easily pluck particles off the surface of the neutron star. So who knows what?
Oh, wait. So if the crust breaks, you can imagine getting out energy radiation comparable to the magnetic field. That's very convenient.
Right.
But you seem to be sitting here that you probably don't have a
Right.
very
So
strong magnetic field, so that
right. So
you're
here the
coupling
field acts as a mediator.
Elastic energy to the magnetic field, but only after the crust breaks.
Yeah, right. So here there's a bunch
That's
of
what I don't understand.
there's a bunch of energy rattling around in the crust, high frequency. The magnetic field basically just acts as a mediator to convert that to particles, right? As you're moving it out. So you're not oversaturating the magnetic field. The magnetic field is just getting energy and then immediately getting rid of it.
I would think that
There's a limit to what you can do though, because you can only sort of put so much power into it.
well, I mean, the fracturing is sort of a reversible process in this context. Where you imagine somehow it's happening.
Yes.
So you have that idea of where we can still have to be happening a lot.
Yes.
But
You have plenty of time for it to reach the shattering.
what? That sounds like it might happen, but that seems to just yield point. No. But whether there's a continuing engine there that keeps on strongly performing at very small scales is not.
No, I agree.
Doesn't all the, if it doesn't feel immediately, doesn't the frequency of the node change dramatically as soon as you have some region of crust?
Yes, but it heals fairly quickly. Okay. Yes.
Along this line, the calculation that you've done is assumes fluid core and solid crust.
Yes.
But actually, the boundary is set up by basically nuclear reaction.
Yes. That's very good. So that was one of the.
Oh, you want to discuss that?
It's one of the caveats, but we can discuss it now. Yeah.
Yeah, so basically, I'm saying if you deform the crust with some frequency, what's the rate that locally the medium adjust? Maybe all you do is just thicken the crust as opposed to.
So there are, as Max is correctly pointing out, there are many reactions that can be occurring in the at the crust core interface, and those things should be things with much shorter time scales than our low frequency should be adjusting as we are perturbing. Okay? So things like the neutron drip reaction, where neutrons sort of drip out of the nuclei, should be occurring much faster than the rate at which we're perturbing this thing. Okay? So that would do something like modify the boundary as we go around. We are currently thinking about this. Tony has done some work on sort of the other side, on the ocean crust, where the boundary can change as a pressure wave goes and melts the surface. And it's roughly equivalent. It basically just modifies the low frequency. Though, it's more subtle than that, but it's essentially that.
Because I'm saying it's not heating the whole.
Yeah. It modifies things. So, like I said, our calculations are more proof of principle. There's many subtleties that need to be addressed. Okay. All right. Okay. So, what we think happens here then is that we get a resonant shattering flare, 1 to 10 seconds before merger. Okay. And that's a nice, neat result. We had to wave our hands a little bit, so maybe we're right, maybe we're not. But what can resonant shattering tell us, if that's indeed what the precursors
You get two, right?
Hmm?
You get two.
Yeah, it depends on how the,
Not at the same time.
it depends on the equation of state, but sometimes they may occur like close enough that you can't tell them apart. Okay, but there's more than just that. Okay, so what can resonant shattering tell us? Okay, well, here a reminder of the structure of the neutron star. Okay, and remember that most of the action occurs right at the base of the crust of the core. Now, one of the big things that we want to get out of studying neutron stars is an idea of what the nuclear symmetry energy is, okay? And also the derivative of the nuclear symmetry energy. That's parameter S is the nuclear symmetry energy. Basically, the energy at the nuclear saturation density, which is like what 0.17 or 16 per Fermi cube, where it's the amount of energy that if you remove, if you have the equal number of neutrons and protons, and then you remove some protons and then change them into neutrons and put them back, that's the amount of energy that it takes to remove one neutron, or one proton and put it into a neutron. Okay? That's what's known as the nuclear symmetry. It's just a Taylor expansion. As a function of the density of neutrons minus density of protons. Okay? And then the derivative of this at that nuclear saturation point. Okay? These are sort of really important. These are really important parameters. You can do a lot of nuclear physics if you know what these parameters are. Okay? Remarkably, a lot of sort of particle experiments. So there's neutron skin experiments. There's dipole for lead dipole polarizability, and a couple other sort of experiments. All sort of map out this little region in here where they all overlap for these parameters. It's actually a remarkable agreement considering how different these experiments are. And astrophysics, the astrophysics constraints, it's a slightly larger region than that, but also maps out about the same region. That's fantastic. You know, what are the odds it'll stay like this? I don't know, but that's pretty good so far. Yeah, so that's the maps out this little region. Okay. This is a plot from Steiner and Watts, paper in 2009, plotting L again versus S, and here they have contours of this is delta R is the skin thickness. The Vs here is the shear speed, okay? And our mode is very much determined by shear speed. The frequency of the mode is very much determined by shear speed. So these are shear speed contours here. So if we draw that same area here, then we map out some region of shear speed that we may expect the shear speed to say. Okay. And note that this is not a this is model dependent. Okay. So it's not like this is definitely the shear speed. It all depends on how you expand around the nuclear saturation. So don't take this as, oh, the shear speed has to be that. It's just that you can, in a model dependent way, map onto the shear speed of S and L. So in this 2009 paper, Steiner and Watts, they looked at QPOs from the 2004 giant flare and tried to use that to constrain the equation of state. Okay? So here is the shear speed, and these are different equations of state. This is that Duchin and Hassel one we used as our fiducial model. And we're actually, well, wait a second. And what they did was they mapped out the shear speed based on all these different models, and then looked at the different QPO frequencies and tried to identify frequencies that those correspond to. Now, unfortunately, because they don't really know which mode was excited, and these are mostly toroidal modes in the first orbital. They can't really, say all that much. They can just say, okay, well, the ones where you have no frequencies or no modes at this frequency, then that can't be. Yeah, but we can't really do much more than that. Now, for us, Andrew was kind enough to give us some equation of state data. And we sort of picked too high, too low, and too high, too medium, too low, just to look at the space of possible being. Okay, and there's nothing special about these except that they're just, I literally said, Andrew, can I have these ones, and these ones? Because one piece. High, medium, low. Okay? And so we plot the frequencies here. These are the mode frequencies where we calculated using the equation of state. And this is a little bit of a different plot. But what happens here is that as this thing, so this thing goes, this is the time for coalescence, and this is the gravitational wave frequency. And as this thing slides towards merger, it goes this way. And merger is actually at infinity down here. This is a lot of fun. At some point, it hits a shattering flare. Okay? Well, that's nice, but what can we do with that? Well, maybe we can detect the change in gravitational waveform. Okay, due to the shattering flare soaks up some energy from the orbit, right? Well, if we look at the waveform and we calculate the gravitational wave change, gravitational wave phase change, it's only about 10 to the minus 3. That's way too small a measure. Even Einstein telescope won't be able to sort of pick that out.
It's a little bit odd because I thought in the end the whole GRP gets, you said it was something like 1,000 of the total energy that you get out of the merger.
Yeah.
Maybe the GRP is just very small. I don't know.
It's very small compared to the gravitational wave mass. So it's too small to measure just using gravitational waves. However, LIGO has a clock, as does Swift. Okay, so with some coincident timing, if we see a precursor flare light off with Swift, or not that Swift will be still around when LIGO finally turns on fully, but whatever we have in the air or in space. At that point, that can do this kind of burst detection. If it can see the precursor burst, then we can do the timing, because if we detect the gravitational wave, we know very precisely what the gravitational wave coalescence time is. Okay? And we can figure out what.
Sorry, very small thing. This precursor should be isotropic, right? There's no
Yes.
real reason for it.
Yeah, more or less isotropic. That's good. Yeah. Stealing my punchlines. Okay, so as we slide along here, we know which, from the gravitational waveform, we know which chirp mass we're on, which chirp mass track we're on. So we slide down, and then time using a coincident precursor burst detection, and figure out exactly what frequency that mode is excited at. Okay? And that will let us very precisely figure out what that mode frequency is, and therefore constrain a lot of the physics of that crust core boundary, specifically the shear speed. Okay? Well, that's the most important part. I'm sure many other parameters involved. But it is so most of the tidal things you can tease out of the gravitational waveform really boil down to mass and radius. Right? So this is just a really complementary measure of the equation of state parameters. One thing to note, though, I think that the maximum influence actually has more to do with the magnetic field than it does with the breaking strain. But strictly, the maximum influence puts limits on the breaking strain factor, because these both go with the epsilon e squared. Okay. I have time for this. Okay. So. Another thing of interest to the community is gravitational wave emission from sort of hyperbolic or parabolic / elliptic encounters. I have my doubts about the rates at which this occurs, but, and I'll get to those in a bit, but there have been several papers published about this, so I guess it's of interest to the community, where you can get a gravitational wave burst signal as things zip past, as two masses zip past each other. You can think of sort of the maximum frequency of that wave burst is going to be related to the periapse passage frequency. Okay? So in order to get pretty close, you have to be pretty close in order to get into the LIGO band. However, that's okay. But if we get that close, if the periapse frequency is bigger than the mode frequency, then we can also excite a mode during one of these passages. And if we can get a resonant shattering flare out of this, then we have a nice isotropic electromagnetic counterpart to a gravitational wave burst. Okay. So this is a preliminary calculation, which I actually did a year ago, but there's some uncertainty about the rate, so I have published it. So if the encounter is close enough, the shattering flare can occur, and the emission will be somewhat similar to the circuit case. And there's some work that's done by Tsang, and some work done by Enrico's group, where you get sort of multiple bursts through these eccentric passages, or parabolic, or single burst through parabolic, or hyperbolic passages. I'll skip over that. The problem really here is with the rates. So this paper claims a rate of about 50 per year per gigaparsec. Unfortunately, they use a neutron star density in Binary clusters that is 1.5 magnitudes too high. And it's based, they made the mistake they made is they used a Fokker-Planck calculation that had really, really fat bins. That only really cared about whether it was an IMDH in this other cluster, and then wasn't actually, the purpose of it wasn't to calculate the number of neutron stars. So they estimated 1,500 neutron stars rather than, 10 or 100. So given that, their rate estimate is about 3 orders of magnitude too high. So a more realistic estimate would actually be about 0.5 to once every 2 centuries. So perhaps this is a pretty, it's not a great thing. However, whoever wrote that stopped them from putting figures out. But one thing that may save this is that they don't. This estimate doesn't include the effect of binaries, of binary single interactions or binary-binary interactions. And you might imagine that binary has a much larger cross-section, so you might be able to get higher rates. Basically, get stuff close enough by changing. Okay. Nuclear clusters may be more promising. Linear closest and low, estimated about, for neutron star, about 1 per year for advanced LIGO. Going through their paper, though, that's super optimistic. Basically, they took every single knob and turned it all the way to 11. And when you do a Drake equation that way, you get a pretty large number. So that's I would optimistically label that optimistic. So encounter rates are a problem for this, and actually this is why I haven't published this paper. But Enrico assures me that they're doing a better job on these Binaries cluster ones now, and their paper's coming out soon, and then so I'm not going to worry about it. It depends on what you mean by C. It won't trigger for things that are 300 megaparsecs. You're not going to trigger Swift. Okay. But if you could see the murder coming from, if you saw the wave burst, you could go back and.
You would need to see gravitational waves.
Yeah. The gravitational wave will probably be a if you have a more sensitive burst detector, then maybe you can do something. But I don't know. That gets into observational strategy, which is above my pay grade. So many things are above my pay grade. Okay, so in summary, precursor flares are seen before some short-term bursts. Shattering flares can be caused by resonant excitation of the anode. And if we have coincident timing with a burst detector and gravitational waves, then we can really probe the frequency of these modes, and therefore probe or get an idea of some of the physics that they crust for them. In future work, we really, this is some caveats here. We really need to get some, the sort of most fuzzy part right now is, as Chris pointed out, how to get that energy out. Why doesn't it just sort of heat up the crust and then nothing happens? And then you just basically get a really hot neutron star that you're never going to be able to see 2 seconds before it merges. Yeah. So getting the details of that emission mechanism is really important. And so far we have basically happening. We do have these precursors though, so something is happening.
You see the precursors scaled up in the duration, of course, in the long burst as well.
Yes, that's true. Those are, yeah, hundreds of seconds.
So bursts are wider and the duration between the precursor and bursts is wider as well. So maybe something missing about the whole population.
Yeah, I mean, that's actually why they went looking for the short burst precursors. This is a long burst. As Maxim alluded to, there's details of the boundary that come from faster reactions that occur at the crust core boundary that you really do need to take into account if you want to get these frequencies right. This paper was very much just to do proof of concept. And in order to actually use this, you need to really get into the nitty-gritty of these low frequencies. And right now, I'm working on this parabolic eccentric encounter paper. And it's very simple calculation. I've already done all the calculations. I had despaired of the rates. So, but now I'm working on that. More papers to do. That's it.
So gravity waves aside, how many of the orphan cracking flares would you expect to see compared with the short?
Depends on the beaming angle of
But there are constraints.
four ones. The problem is that they're much dimmer, and we don't really know how it depends on the magnetic field of the neutron stars. And there's got to be a strong dependence on the magnetic field. If you have no magnetic field, you can't get the energy out at all.
You just assume that the precursors you saw were.
Well, 1 out of 40. No, sorry, pardon me. 3 out of 40 of these short gamma ray bursts that I looked at had precursors. So you can extrapolate based on that, I guess. So if those are standard neutron, if that's a standard population of these neutron stars, then maybe 3 out of 40 would be able to have the shattering. You'd be able to pick out these shattering fires.
You would see 30 times more, right?
Yeah, but then you'd see 30 times that. Well, depending on the roughly, yes. Yep.
Instantaneous release of 47 photons in the sphere would make it very similar to the giant flares, which have quite a definite profile, intensity profile.
Yeah.
How does it compare with the duration?
So it's not quite the same. If the magnetosphere basically just exists as if you're just transferring energy through the magnetosphere into a fireball, then it's not going to be quite the same thing as a giant flare. Plus, the magnetic field is much higher in the giant flare case. So I don't know.
There is this generic capacity problem.
Yeah.
It releases so much energy that you will make pairs.
Yeah. So, how does I mean, you can look at the data of these is not great, so I don't know if I can answer your question. I mean, can you tell much from the profile of that? And it's, like I said, I'm surprised that they claim these are 5 sigma. So, I don't know if that answers your question, but.
No more question for Dave. We can continue discussion upstairs with cookies. We'll take Dave for dinner tonight. I guess I'll send an email later on in the afternoon.
So, I also just finished some work on timing noise and pulsar timing noise in magnetospheric molar inertia. So I'd be happy to talk to anybody.
Will you be here on Wednesday?
I'll be here all week.
We've asked for PH on Wednesday.
Okay. Okay.
I would be prepared.
Yeah, I think that's a week without sunshine. Okay. So yeah, and I can also talk about some black hole disk oscillation work that I've done with the undergrad at Caltech, just in the last few months. So, which isn't